right. So today we have Andrea Boido, who will tell us about matrix models from black hole geometries. Take it away.
Okay, thank you, Julius, and thank you for letting me speak here at the Quiver Meeting. So I'm gonna talk about this project we've been doing with together with my supervisor, James Sparks, and also Alice Lusher, which is another PhD in Oxford. The paper will hopefully appear soon. I'm not sure when, but hopefully soon. Okay, let's start with a brief outline of what I'm gonna tell you. So I need to do a disclaimer. Unfortunately, there's a lot of background material that is sort of needed to get to the point. So we'll have to review a few things. In particular, the second and third section are mostly review. I'll try to, I'm gonna be quite schematic on those, but I'll try to highlight like the main points, takeaway messages. So first we're gonna speak about three-dimensional n=2 superconformal field theories and their Lagrange limit, and then their dual ideas for black hole geometries. And then the new stuff will arrive mostly in 4, while I will tell you what's about this holographic dual of the matrix models, and then we're gonna go to some wrap up. I also put some references in, especially in the review section, but these are far from being a complete set. Like there are too many, so please, I hope you won't complain about that. Okay, let's get started. First, some context and motivation. We are working in ideas for CFT3 correspondence, so you should have in mind the usual pictures of putting a stack of, in this case, M2 branes, the tip of a conical Calabi-Yau fourfold. I'm going to call it X4 here. And this is a cone over a Sasaki-Einstein manifold Y7. And okay, you can, on one hand, you can look at the word volume field theories, which in general are three-dimensional n=2 superconformal field theories. But on the other hand, also you can like let the brane back react, and then you have pure geometry. And in this case, you will end up with empty ADS4 times this Sasaki-Einstein Y7. Okay, next thing you can do is then you can you can wrap your branes on a Riemann surface with no punctures, genus G Riemann surface. And this in field theory corresponds to put the field theories on the Riemann surface as well. And I'm also gonna compactify the Euclidean time to S1 in this case, so that we can, in a second I'll tell you, but we can perform localization. In geometry, what happens instead is that your geometry gets replaced by this ADS2 cross Y9, where Y9 is in general a fibration of the Y7 we had before on the Riemann surface. And this geometry, in general, understood to be the near horizon limit of some supersymmetric ideas for black holes. Okay, as I was telling you, in field theory, you can perform localization to compute the partition function, and then you can also take the Lagrange limit, which is what we want to do because we are doing a SCFT. And the resulting thing you have is a matrix model, and from that you can extract indeed this partition function Z. On the other hand, in geometry, there are many ways to compute the entropy of these black holes, but I have in mind this formalism of GK geometry, which you don't really need to know precisely what it is, but yeah, I will tell a few words about that later on, but in general, my point here is just that you can compute the entropy of these black holes, and rather unsurprisingly, these two quantities match up to taking the logarithm of the partition function. What we discovered is that actually there's another matching even further up these arrows. In particular, like in the matrix model, when you do localization, you have some function which is called the eigenvalue density. I will tell you what it is later on. And this function is mimicked by a particular geometric quantity, and that's the subject of this talk. I didn't say that before, but of course, feel free to stop me at any point for questions. All right, so let's jump into the first part. So the three-dimensional superconformal field theories. Okay, in most of the talk, we will focus on the 11D geometries, but I need to go back to type 2A now, to the geometric engineering of these field theories to motivate some of the results we have later. So we consider this geometry in type 2A. We have a flat space R12. And then we have like this time still a conical Calabi-Yau, but it's a threefold this time. And then we have a real line, which I'm calling RT. And we put some ND2 branes in the along the flat direction. And this setup here will generally give rise, well, under some assumption on the X3, but will give rise to some three-dimensional n equal to Quiver description of field theories, and this will have a gauge group U1 to the G. For the purposes of this talk, G will either be 1 or 2, but still, in general, we have this structure here. So, like this field theories will have G vector multiplets, and in this vector multiplets will be, of course, the scalars, which I'm going to call sigma I. Yeah, with I going from 1 to G. And like this thing, I mean, I don't want to tell you much about these theories, but like something which is rather important is that in the moduli space, these scalars are all equal to each other. So sigma is equal to sigma G and is equal to simple sigma. And since these are n by n matrices, like they're also, in this case, they are also diagonal. So yeah, I'm going to call the eigenvalue sigma 1 with the one subscript and to see up to sigma n. And the important thing, the takeaway message of this slide is that the eigenvalues of this sigma in the moduli space, sigma alpha, is the the sigma alpha is the position of the alpha D2 brane in the RT direction. So yeah, you can see here I have the I put an X there. Okay, this is a general factor of geometric engineering, and that's what you need to remember about this slide, basically. Okay, on the other hand, when we have this geometry, we can uplift that to 11D. We have an M-theory circle, which we add to the geometry, and then we will end up with what I was telling you before. So R12 cross X4, and then the D2 branes will be interpreted as M2 branes in this case. Sorry, okay. And in particular, once you have this M-theory circle, you will have a U1 isometry, which I'm calling here U1M, which acts on the Calabi-Yau fourfold. And this will be generated by a killing vector, which I'm calling here zeta M. And so you can recover then the type 2A geometry by quotienting with respect to this U1M action. Yeah, in general, note that like you can start from the same 11D geometry, but choosing a different M-theory circle, you will end up with different geometries in type 2A. Also, yeah, sorry, that's okay. I don't know why, but the slide is okay. This is a DMU, sorry. Okay, let me define here like an important quantity. This will be crucial for the rest of the talk. And this is the moment map. And this is just a function that goes from the internal space in M-theory X4 to the real line R. And is defined to be such that its differential is equal to minus the M-theory circle generator contracted into the Kähler 2 form on the X4. And yeah, this is also, again, this is important for the rest of the talk. And one fact that I'm not going to justify, but you can see that the image of this moment map is actually the RT line that you had in the 2A geometry. All right. Okay, let's see an example for a second so to have more clear what's going on. And then I chose probably the most simple field theory you can think of, which is ABJM. So you in 2A, you just you use the conifold as an X3. And when you uplift it to M-theory, the Calabi-Yau fourfold is just C4 mod ZK in this case. And this will give rise to indeed the ABJM theory that we all know. And so we have two gauge nodes, both UN, of course, with this superpotential that I brought here. Now, if you introduce like the most easy coordinate you can on C4, so ZA you can call them like the modulus of Z times some angular direction, and A goes from 1 to 4, of course. Then, okay, the generator of the M-theory circle in this case is given by this vector that I wrote here. So it's a linear combination of the vectors that rotate each coordinate. The Kähler-2 form on the Calabi-Yau cone is also the standard one, and is given here. I mean, okay, these formulas are not particularly important. It's just to show you that it's fairly easy to implement these in certain cases. And then from the definition of the moment map that I gave you before, you can read that the moment map is the thing that's written at the bottom of the slide. And yeah, and again, like if the coordinates, of course, are unrestrained, so the image of this moment map is clearly R, as I was telling you before. All right. Okay, now we have these field theories. We want to put them again on S1 cross sigma G and perform localization. Yeah, okay, we put them with a topological twist, of course. And as I was telling you before, the partition function localizes. In general, the localization locus is fairly complicated. You have to sum over gauge fluxes and whatnot, but I mean, we don't need any of these details here. What's important for us is that in the BPS locus, you have that this sigma I, and also which is the scalar, which are the scalars in the vector multiplet, and also the component of the gauge fields along the S1 are not vanishing. And in particular, it's convenient to repack them into this UI that I wrote here. So this is just yeah, the gauge field plus I, the scalars, and there's also a beta appearing there, which is just the length of the S1. Yeah, and these UI are also diagonal in the localization locus, and so yeah, you have n of these for each of the I. Sorry. Okay. The important thing now is that not any such configuration contributes to Z, but by doing some residue analysis, you can see that the UI, sorry, that contribute to Z are just those that satisfy this equation here, which I'm calling beta ansatz equation, and actually equations because there are more than one. And yeah, again, it's not super important the form of this equation. They're particularly complicated. This capital U beta is what is called the beta potential. And the important thing of this is that it depends of course, on this UI, but also on something that I'm calling delta phi, which are some trial chemical potential for the field phi. So the phi here is a general field of the theory. Yeah. Okay, this delta, I'm gonna call them also trialar charges sometimes in the talk, and that's because they're closely related to what are the trialar charges in the equivalent picture on S3 rather than S1 cross sigma G. So yeah, I'm gonna confuse the two concepts so far. Sorry, in the following. Okay. Yeah, okay. As I said, the beta ansatz equation are fairly complicated to solve, but we don't really we don't care too much about that since we're again doing holography. So we want to look at them at large n, and at large n you can perform some numerical simulation and formulate an ansatz for this equation. And in particular, the ansatz that is proven to work is the one that I wrote here. So like the imaginary part of this UI, of the eigenvalues of this UI will all be the same, and will scale like n to the 1/2. And then you will have a real part, which is encoded in this VI alpha. Okay. Okay, then if you take n to be infinite, then these eigenvalues will become dense, because you have more and more of them, and will become dense, and in particular, they will be continuously distributed inside an interval, which I'm writing here. We'll introduce this t without any subscript, which is now a continuous variable, and this will be distributed in this interval t min t max with this density, probability density rho of tau, or rho of t, sorry. And in particular, this means that like the number of T alpha in any interval will be given by this formula here in the between brackets. Okay, so when this quantity become continuous, then like u and v become functions of t, and again t will be a variable, as I wrote here. Oh, sorry. Okay, now with these ansatz, we can solve the Bethe-Ansatz equation. It's not particularly difficult now. And we solve them in particular for rho of tau and for vi of tau. Of t, sorry.
Question?
Yes.
What is the ensemble you are considering?
Sorry, can you say again?
What's the ensemble you're considering?
I think it's the grand canonical.
So I'm lost here. Can you show before how did this show up? The density?
The density? Yeah, the density is I mean, it's just because okay, you have these quantities here, these ui alpha, which are the eigenvalues, and alpha takes value from 1 to n. So when you send n to infinity, you have infinite many of these alphas, of these ui, and it turns out that essentially this T alpha gets continuous.
Okay, so you're considering some large n. So you have an ensemble of many gauge theories parameterized by n. You take n to infinity.
Yeah, precisely.
And you consider the parameter t to be a continuous variable in this limit.
That's what's going on. That's what is being like found in these papers that I quoted here at the bottom. Yeah.
Thank you.
Yeah, no problem. Okay, yeah, sorry. I was saying, okay, with these ansatz in hand, your Bethe-Ansatz equation become easier to solve, and you can solve them. And the important thing that you find is that this rho of t, sorry, which is the quantity we will be studying later, is a piecewise linear function, and of course it will depend on the chemical potentials of the fields. Now, okay, this may sound a little bit abstract, but then like I show you for ABJM what's going on, actually what's the result already. You do all what I said for ABJM, you find that this function of tau is this nice function here. And in particular, like, yeah, I'm not displaying the full expression of this because it's a bit involved, but I mean, it doesn't really matter. The important something which you can see here is also that you have particular expressions for these points where the function, well, the derivative of the function is discontinuous, and these are given in terms of this mu that I brought here on the side. But yeah, it's just everything is given in terms of the of the chemical potentials, and on, of course, k, which is the k in the zk quotient in the geometry. Okay. So yeah, what we want to do in the end is reproduce this function from geometry. So let me already tell you what's the main idea that we followed here. And going backwards, we have this variable with this continuous variable t, which arised taking the large n limit of this T alpha. Now, these T alpha are clearly directly related to the sigma alpha, which are the vev of the scalars in the moduli space. Sorry, in the localization locus. And this is because, like, you see that UI is defined as the quantity which I wrote here on the right. But then when you take the large n limit in, your ansatz is the one on the left. So the imaginary part is clearly relates T alpha with sigma alpha. On the other hand, as I told you, like these scalars here, like in the geometric engineering picture, parameterize the position of the D2 branes that you started with, which in the RT direction in the geometry. And this RT, as I told you, is the image of the moment map. So it's clear that T here will be somehow related to the moment map. This is very hand wavy, like I'm not saying this is a rigorous derivation, it's just heuristic, but that's served well as a motivation of what we will do. Now, before making this a little bit more precise, let me go and explain and tell you something about these geometries we're considering. All right, so, okay, as I told you already at the beginning, you can make the brains backreact on the space, and the geometry you end up with is this ADS2 cross Y9, where Y9 is a fibration of a Y7 over the Riemann surface. And Y9 is also what is called the GK manifold. Again, you don't need to know precisely what that is. I'm gonna say a few things later maybe, but yeah, it's just for those who know. And okay, this geometry though is also like the near horizon limit of some black holes in the following sense. You can consider some supersymmetric black holes in ADS4, and in particular, we want to consider black holes which have as horizon ADS2 cross Riemann surface. And also we want these black holes to be magnetically charged, and with these pi, which are the magnetic charges. Then you can uplift these black holes in 11D on this Sasaki-Einstein manifold Y7 that I told you about before, interpreting the magnetic charges now as twisting parameters for the how to fiber the Sasaki-Einstein space on the Riemann surface. The near horizon of these black holes will be precisely the same thing I told you before, so ADS2 cross Y9. So that's why I'm saying that this is that we are going to consider the black hole geometries. All right. Yeah, sorry. This vibration structure is pretty important if you want to reproduce the whole, like if you want to match the partition function with the entropy of the black hole. But for what we are interested in this talk is actually what we care about is essentially the fiber, not the whole geometry. So let me tell you a bit more how is the fiber. So okay, we start from our cone over Y7, which, as I said, is a Calabi-Yau fourfold, and has Kähler-2 form J. You can write the metric on it as a simple cone metric, of course, and then you will have that your Y7 is embedded at R equal to 1. And the important thing is that there is a particular U1 action on this Y7, which is generated by a vector which I'm calling Xi here. And this I'm going to call the R symmetry killing vector. And the reason why I'm doing that is that when you do a holography, this is dual to the U1 R symmetry of the field theory. So in particular, once you have this vector, you can see that you can actually build your Y7 as a fibration itself. In particular, it will be a fibration of this U1 Xi over a Kähler space, six-dimensional Kähler space, which I'm calling K6, and whose Kähler form is this omega here, and it's simply given by, I don't know what happened there, but anyway, it's given by this omega, which is given by J restricted to R equal to 1, rather unsurprisingly. Okay, now let me do a remark about extremization. So all that I said so far, like in field theory, was a sort of off-shell in some sense, given that like the chemical potential we have, delta phi, are generic. Then the picture you should have in mind is that you wanna in the end extremize over these deltas, and that's what is called I extremization, to get what leads you to the superconformal R symmetry. This procedure is mirrored in geometry by some geometric extremization principle, where in particular we want to go off shell, but still retaining some supersymmetry in the geometry, and that's achieved by, for once, deforming the Kähler form in this way. So we introduce an extra parameter, big lambda, capital lambda, which is a real parameter, and it will be later on fixed by some flux quantization condition. Okay, and then also your R symmetry vector psi will not be a specific vector, but so far it will be just a linear combination of all the possible U1 that you have, U1 isometries of your internal space, Y7. Okay, then once you've done that, you can mirror the procedure by extremizing over this psi, and you get the on-shell geometry in that way. Our result is purely like is achieved off shell, so we don't need to actually go on shell later on. You can do that, but it's not needed. So we are working with generic chemical potential and these off shell geometries. All right. So what is our ABJM theory of shell? So okay, you recall that we introduced these coordinates ZA on C4 mod ZK, and clearly this space has U1 to the 4 isometry, which is generated by these, of course, these killing vectors here. Then you can parameterize your R symmetry vector in this way. So you just sum over these. You just consider a linear combination of these U1 to the 4 isometry, with parameters which I'm calling RA. And this array in particular will be directly related to the delta phi in field theory. But yeah, I'm telling you later the precise identification. And then, okay, if you go off shell, then this will also change what are your Kähler form and your moment map. But there's a convenient set of coordinates that we can introduce, which are these YA, and this will simplify a lot our expression. And these are just like each YA is related to each ZA in this particular way. But the important thing is that these will be all positive because they are modulus of something. Then, okay, you have various expressions. You have your radius will be this thing here. Your Kähler form will be this, and your moment map is similar to what we had before, but in terms of the Y, this is even simpler. All right. Okay, we are now ready to talk about the new results. So, if you remember, I told you already that.
Sorry, can I ask you a question before that?
Yeah, sure.
It's about this off-shell versus on-shell
Yeah.
business. So what I don't quite understand is that in the field theory, I can define the field theory on a curved space with any R charge assignment. That's a choice. And then this should have a gravity dual, which is on-shell, not off-shell.
Yeah.
So what is the deal here?
So I think this whole business is not quite understood precisely. I think there are some results in the literature where they also essentially consider some deformation of these geometries that are actually on shell, but they are different deformations, and they are supposed to be dual of these field theories with generic R charges. But like, yeah, the picture I'm using here now is a precise one, which is the one of GK geometry, as I said already. And yeah, I'm not sure how to justify this physically. Like what you do essentially in the geometry side is just like you impose the supersymmetry of the space. So you have some killing spinors and you study their bilinears. But then you lift some condition, which you lift essentially one of the equations for motion. And yeah, and then you see that you can perform this procedure and go on shell. Like I don't have a more detailed interpretation of this physically, let's say.
Thank you.
Yeah, no worries. Are there other questions, by the way? Okay, let's go to the new part. Yeah, as I told you before, we said already that this variable t in field theory, which is the thing the eigenvalue density depends on, is somehow related to this moment map. In particular, we need to introduce the thing which works is this restricted moment map, which I'm introducing here. So it's essentially the same thing, but defined on Y7 rather than on the whole X4. And so, yeah, it will satisfy this equation with omega rather than J. In particular, once you have deformed your geometry, you see that this HM is given by 2 lambda times mu m, and then you restrict that to r equal to 1. Okay, now in particular, we know that Y7 is a compact space, so the image of this function will clearly be interval in the real line, and I'm calling this I with extreme tau min and tau max. Okay, but this is good, like, because the support of rho is also an interval, as I told you. In particular, if you identify tau and t in this way, with where LP is the Planck length and of course is the number of branes, then there is a precise matching between the two things. Okay, that's good, but we can actually do better. So I need to introduce this new space. Okay, if you recall that I told you that Y7 it can essentially be seen as a U1 factor and then a Kähler 6-dimensional space. So you can introduce this new space K tau, which is defined as a symplectic quotient of K6 by the M theory circle action. And okay, you don't really need to know precisely what a symplectic quotient is, but like more, let's say, easier way to think about it is just you restrict yourself to the level set tau of the moment map, and then you do a normal standard quotient by the U1M action. In particular, this has some consequences. They are pure mathematical consequences. The first thing is that this K tau is a Kähler manifold itself and is a 4-dimensional one. In particular, you remove 2 dimensions from K6. And the Kähler form, I'm going to call omega tau the Kähler form on this space. Then the second consequence is that the interval, which is the image of the moment map, is actually split in subintervals, Ik, as I'm drawing here on the right, and the extrema of this interval, which I'm calling tau k, are precisely identified with the points with the value of the moment map in the points in the critical points of the moment map itself. So where dh is equal to 0, which, like, if you study its expression, you will realize that it's also when the M theory circle action is the M theory circle is aligned with the R symmetry circle. And that's also quite intuitive because like to restrict to your space K6, you sort of had to quotient with respect to the U1 R symmetry circle. So when this condition is true, the one of the Zm to be aligned to Xi, these are sort of fixed point of the action of Zm on the K6. This is this fact that we have the splitting in subintervals is also good because also the support of rho is naturally split in subintervals, which are corresponds to the let's say the patches where the eigenvalue density is linear. Okay, in particular, omega tau, so the Kähler form on the symplectic quotient, is linear in tau in each of these subintervals. But this is also very good because, as again, rho is also linear in these intervals. Okay, so you can think, well, our rho of t will be sort of omega tau. Well, this is a bit quick because, of course, rho is a function, omega is a form. Doesn't make much sense. You can try to integrate this omega tau over some space, but it's not clear which 2-dimensional space you would pick. We don't have any natural choice. So the next thing you can do is square the omega tau and then integrate over k tau, which is 4-dimensional, and that makes sense. And this is actually more or less what you do, but then it's not anymore linear. And to recover the linearity in tau, you need it turns out that you need to take a derivative with respect to this parameter lambda that I introduced before to deform the Kähler form. So this is the final formula that we found. So yeah, you take the derivative with respect to lambda of this integral, and this integral is nothing but the volume of the symplectic quotient. Okay, yeah, I'm not writing equal, I'm writing sim. That's because you need to fix the normalization by requiring that this density is integrates to 1. That's purely field theoretic, let's say, constraint. actually mathematical constraint because it's a probability density in the end. Okay. Okay, we have this formula. Now we should think, okay, how do we compute this volume of k tau? Well, there are many strategies. You can do it directly, case by case, and that's what I will show you next for the ABJM theory. You can try to use toric geometry, and we actually did. I have a few comments on that later on. Another thing we thought about, but we haven't tried so far, is to use some equivalent localization formula. There's a formula from Jeffrey and Kirwan, I think. That also should probably work, but we haven't tried that yet. There might be other ways, but yeah, that's the one that we came up with. Okay, so let's see how this works concretely for our BJM theory. So recall that we're using these coordinates, YA and phi A on our space. YA introduced them before, and they are positive. And in particular, these are sort of decoupled coordinates. So like the YA, they just parameterize R4 with some Euclidean metric. And then the angles phi A will contribute with factors of 2 pi. So in the end, we are sort of mostly interested to the first part. Our k tau in this case is defined by, well, firstly, taking the radius to equal to 1. This localizes us, well, not localizes, but like puts us on the Y7 space rather than on the full cone. And then, of course, we will need to impose that the moment map is equal to tau because we are restricting to a level set of that when we do the symplectic quotient. Okay, the first equation is actually pretty simple and defines a tetrahedron in R4 with vertices, which I'm calling PA, which are given just by, well, okay, I missed something. It's RA to the -1, and then you have the canonical basis of R4. Okay, I can't draw in 4D, but if you go to 3D, you can see this pretty clearly. Like this equation here on the left defines you a plane. This plane will intersect the axis in these points P1, P2, and P3. And then you should remember that YA are always positive, so we have to restrict to the positive octant of the space, and this identifies precisely a triangle. Okay, when you do the same thing in dimension 4 rather than 3, you get a tetrahedron. Okay, so let's study now the second equation, so the one with the moment map. We have our tetrahedron here on the left. The equation that you end up with is here at the top, and this describes another plane, another hyperplane in the space, and this plane will slice the tetrahedron. And in particular, when you change the parameter tau, this will move the plane parallel to itself. Here I have a picture of this. So in this picture, tau is sort of going in this direction, more or less. So yeah, when you increase tau, you move from left to right, essentially. Okay, so when you cut this tetrahedron with this plane, you will identify some polyhedron. In particular, there will be either a triangle or a quadrilateral. And I'm calling this Q tau here in the picture. And yeah, essentially the volume of your symplectic quotient, k tau, is proportional to the area, to the Euclidean area of this Q tau, which is easy to compute using standard linear algebra tools. And then it turns out that when you take the derivative with respect to lambda, you actually compute in the perimeter of this space. Okay, so you can see from this picture that then you start from when the plane identified by imposing the moment map to be equal to tau. You start when this plane is on P2, let's say, and then you can start move towards the right. It will be identify a triangle. Then at some point, this plane will touch P4. It will, like the point identified there will split and will become this Q tau will become a quadrilateral. Then you keep going right. At some point, this will touch P3, and it will become again a triangle, and then go all the way to P1. So from this picture, it's also clear that the points that delimits the intervals ik correspond essentially to when the plane intersects the vertices of the tetrahedron. Okay. Here I have so the computation that we did, which is pretty neat. Okay, yeah, sorry. Here the two pictures are not like exactly related to each other. Like it's more of a okay, that this is what you should expect to get, but don't try to look precisely into these two pictures. But anyway, so yeah, essentially, if you compute the perimeter of this Q tau, you find that okay, it's at the beginning it's 0, then it keeps increasing in this red part up to the point when it becomes a quadrilateral, and then it changes linearly again, and this is the blue part, and then again it becomes again a triangle in the last tail here. And you can compute this very explicitly in terms of your RA, and you see that there's a perfect matching with the field theory result. Again, I'm not writing the full expression here because they are pretty nasty, but yeah, if you identify their charges in this way, okay, you have a precise identification, of course, of R1 with one of the deltas, and etc., but it's not really the point here. And also you see that this lambda that now is sort of on shell because I imposed this flux quantization I was telling you before, is given by this expression, which is clearly related to the mu that I had before. Okay. Also, let me tell you that I was telling you before that this sort of points where the derivative of rho is discontinuous are related to are points where the two U1 vectors are proportional to each other. And in particular, you can see that here, like for instance, this first point on the left is the point in Y7 where the Y1, Y3, and Y4 are 0, and in this particular point, your ZM is, and both your ZM and your Xi are proportional to d by d phi 2, and so yeah, that checks out. All right. Okay, let me sort of tell you a bit more about our conclusions and what works and etc. Some other things I didn't mention. So, okay, the takeaway message here is that when we you have your geometry, you take the symplectic quotient of your Kähler space with respect to the U1M action, and this will give you your eigenvalue density essentially. Okay, we tested this actually in many examples, not only in ABJM, but yeah, in ABJM it works. Now for Y7, for Y7 equal to S7 mod ZK, which is the case for ABJM, you can also choose a different M-theory circle, which is this one, which will give you the ABJM quiver instead, rather than ABJM1. And this corresponds to slicing the polytope in a different way. The polytope is still the same tetrahedron you had before, but you are slicing it differently. I have actually a picture later if you want, but yeah, otherwise it's fine. Then we also tested this for other toric cones. It should work for any of these. We tried like there's a very general formalism that lets you do this computation, and we tried that for the cone over Q111 and also C times the conifold. Okay, and this essentially amounts to changing what is the polytope you are considering. So rather than a tetrahedron, you will have some different polytope, but you still have the picture where you can slice it with some plane, and the polyhedron you are I mean the geometric picture in 2D that you're identifying is the volume will give you the eigenvalue density. Okay.
A question.
Yes.
So in the generic case, the circle action have fixed points.
Yes.
That's what I would expect. So how does that affect the general story?
Wait, sorry, which I didn't get which circle as you said that is
the circle action, the one the U1M.
Yes, the fixed point of the U1M gives you precisely these points here, let's say. Like, yeah, because in general,
So I don't quite get that. For ABJM, I mean, that circle action has no fixed point, the one that you're
okay, yeah, sorry.
Picking
okay,
to go to type 2A.
I got the point, sorry. I was
Whereas for
because,
Q111, I should have...
Yeah. No, you're right. It's just because like these are also fixed points, but they're fixed points on K6 rather than on Y7. So, but yeah, you can have indeed also points on fixed points on Y7, and these essentially correspond to the insertion of D6 branes. And from the point of view of the matrix model, these are not particularly different from this, meaning that even also in that points, you have a discontinuity of the derivative of rho. So this Kuspitz, let's say. I think all those cases corresponds to discontinuity in tau equal to 0. But yeah, they are not particularly different from this in this perspective.
Did you also look at cases where the D6 brane wraps a compact first cycle? Because in that case, the story is quite different. And back in the day, people didn't quite understand the matrix models, and probably it needed different ansatz.
No, we didn't look at those cases, just the standard ones, let's say. Yeah.
Thanks.
No worries. So yeah, I was saying for toric case in general, you will have a different polytope. I also have some figures for those if you want to see them later. And yeah, you will have a slicing of this polytope, and the 2D figure will give you the eigenvalue density. Okay, you can also try to, like the formula I showed you before, in principle holds even for non-toric cases, the one with the derivative of the volume of k tau. Unfortunately, we didn't try any of these examples. For instance, like you can think of trying the column by P52. I think that it should be feasible to do that using again this equivalent localization that I mentioned to you before. But again, we didn't try that so far. Okay, now let me also mention something which we also looked at in the paper. Which I didn't mention before. Like it's interesting because you can also map these sort of discontinuity points to some classical action of problem 2 branes. In particular, you can consider problem 2 branes that wrap the ADS2 factor of the geometry and the M-theory circle. And you can study the BPS condition of these branes, and we did that. And it turns out that these are BPS precisely in the points where zeta m and psi are aligned, which again, if you remember, is the same as the critical points of the moment map. And yeah, and you can see that the classical action of these M2 branes, here K is like the sort of the kth locus where these are BPS, will match precisely with the tau k, well, up to the Planck length, but yeah. And yeah, so essentially, if you interpret these M2 branes when you reduce to 2A, and these become fundamental strings because now they're wrapping the M-theory circle, their action is also supposed to give you the dual of the valve of a Wilson loop in the fundamental representation. So it's interesting because like these points, like the minimum tau gives you also this what I just said, so the valve of this Wilson loop. Yeah, it's another neat thing that we discovered. Well, sort of this was actually very much inspired by some earlier work that James did with one other of his students some years ago on S3 rather than S1 cos sigma g. But this works also for S1 sigma cos sigma g. Finally, okay, let me mention briefly something which we looked at fairly recently. These are a partial result. So like you can try to replace your Riemann surface with a spindle, which is this space with which topologically it's a two sphere, but it has some conical singularities at the 2 poles, which are not, you cannot get rid of them because they're parameterized by different integers. Okay, there's quite a bit. There's been quite a bit of results about spindle solution in the last few years, but in particular, it's sort of clear now that they describe the solution of this kind with the spindle instead of the Riemann surface, describe black holes that are also accelerating. And then you can try to do the same, can try to apply the same ideas to that case, but that's a little bit more difficult because in that case, the R symmetry vector mixes also with the U1 isometry of the spindle that rotates it around its axis. And also, like, if you want to try to do this off-shell, let's say, off-shell extremization of the geometry, you need to introduce two parameters for the Keller form rather than one. So the picture is quite different. And we don't have a clear interpretation at the moment. What we sort of believe is that essentially you have a factorization of these matrix models into two independent ones that lives on the poles of the spindle, the plus pole and the minus pole. And essentially, because essentially the geometry over these poles is not that different from the one, the local geometry is not that different from the one we had before with the Riemann surface case. So you can think of taking the same eigenvalue density you had before, which I'm calling here rho sigma g, and perform a sort of a shift of the R charges in a particular way that I don't have time to get into, but essentially you replace this RA with this RA plus minus, which are quantities natural in the spindle geometry. And then you get two separate eigenvalue densities, which I'm calling rho plus and minus here. And yeah, and somehow from this, we think it's possible to recover the full rho, although at this point, we still don't know precisely how to do that. But like this picture is also backed up by the M2 brains computation, because like they're like studying the problem M2 brains, it's doable, and we did that quite precisely, and we found that like these fixed points are essentially at the two poles of the spindle, so it makes sense that sort of you have two matrix models at these poles. But again, we don't know precisely how to recover the total rho from geometry. All right, yeah, let me conclude with some open questions that I think this project has raised. Well, first of all, I mean, this all what I told you is neat and it works. It's very geometrical in a sense. So like we don't have let's say a physical interpretation of what we are doing in terms of, I don't know, brains of some kind. Like we thought about that a little bit, if like these there were, I don't know, some brains that could wrap these k tau that I introduced before, but it's at the moment it's still not clear what's going on. Then you might also ask yourself, well, we were able to reproduce this rho of t from gravity, from geometry. Why can we do better and reproduce also this vi of t and the beta potential? This, if you remember, is the real part of the of the holonomies, let's say, in the matrix model. And yeah, I don't have much to say about that as well. Like I thought about it a little bit, but this function is a little bit more complicated. It's not just a linear function. Yeah, I don't know how. It could be conceivable that it's possible, but I don't know how to do that. It would be interesting to study this problem, though. Well, then related to the last thing that I said, of course, we would like to study more precisely these matrix models on the spindle. This is also because at the moment there are no field theory results about this. Like I think the index on the spindle has been studied using localization, but nobody has done the Largen limit yet. So it would be interesting to understand better what's going on there. Yeah, and finally, okay. Finally, yes, you can think of different field theories. Like there are other three-dimensional field theories where you can do localization and use these kind of matrix models, but these are not dual to M theory, and for instance, a different scaling of with the number of brains, let's say. For instance, I brought here the massive type 2A theories. These have n to the 5/3 scaling. And I mean, the matrix model in the end is quite similar, but it's not clear to me how you would apply these ideas there, because like you don't have any M theory circle, and which is quite crucial for what we did in this project. So yeah. Yeah, I think I'm actually done. So yeah, thank you for your attention. And if you have questions, I'm happy to discuss.
All right, so let's thank Andrea. Very nice. And yeah, do we have more questions?
Well, I guess I can show you some more polytopes if you want.
Oh, wow, okay. More.
For instance.
Oh, this is neat.
Yeah. This is the ABJM. So like it's same polytope as before, but you have a different slicing. And as you can see, like the blue Q tau is parallel to one of the edges, and that's precisely where you have a D6 brane in field theory. So that's probably related to what Stefano was asking before.
A fixed point in Y7, not K6.
Yes, indeed. Yeah. Here I also have the full row for if you're interested.
So is the K tau, is this always smooth, or does it get singular?
No. In general, it's not. Not even K6 is always smooth. K6 can have singularities, yes.
Oh, I see. Okay, yeah, sure.
Yeah. But I've been actually, if I can say a little bit more, like I've been a bit sloppy here, because like in general, the U1 psi action, like U1, the U1 psi is not always like the orbits of this of the vector field that implements these not always close. So when you sort of quotient Y7 by this U1 psi, you might get a mess, not necessarily this neat Keller space, which is not smooth, but anyway. But the way to get around this is that sort of you can consider these for rational values of the parameter that parameterize your R symmetry vector, and then everything works because these orbits close, and then you extend by continuity to the irrational values, let's say. And yeah, but then also like if you go when you go on shell, you perform the extremization, they're always rational, so it's a bit of a technicality. It's not really that interesting. Yeah.
What kind of geometries did you put? What kind of singularities did you look at?
Yeah, the one that I said, where was it? Here. So essentially, we considered the these, and so ABJM and BHM, and then these two toric spaces. In particular, also here you have two different choices of M theory circle. Actually, I have the plots of this as well. I can show you.
How about the closure of the minimal nilpotent orbit of SL3?
Yeah, we didn't look at that. Yeah, I don't know.
That's one of the simplest four-dimensional varieties, or complex.
Yeah, I don't know. Yeah, we can definitely have a look. We haven't so far, but yeah, if it.
You looked at the toric cases, right?
Yeah, mostly that. Yeah. Also, like I mean, BJM, like I sort of lied a bit because I did you all this process, but you can. It's of course it's toric as well, so you can use the toric machinery. It's very neat how it works.
Where was this essential?
Well, you have these sort of polytope pictures where you have this polytope and you cut it only in the toric case. If you don't have if it's not toric, like we don't have this neat picture, and yeah, again, I'm not sure how to compute this volume. Well, apart from what I told you already, so trying to with localization or I don't know.
It affects the computation of the volume?
Yes, I mean you can compute this volume of k tau in various ways, I guess, and with the toric formalism, it's very simple to do. Yeah.
So that's the only physical quantity which requires the singularity to be toric?
Sorry, what's... I don't think I got the question.
Is this the only physical quantity which requires the singularity to be toric?
But I wouldn't say that it requires, I mean, like the formula we had here, wait a second. Okay, this formula here, in principle, does not require the toricity. I'm just saying that we didn't try to use it in any example which is not toric. But we believe that it should work.
I see.
Yeah, but it should work even if it's...
But you also had a case there which doesn't look toric. Can you go back?
Where, sorry?
It is toric. Okay. You showed set of examples.
Oh, yeah. Sorry. It's later. Here.
It was the...
Yes.
5-2. It's not...
Yeah.
Okay.
Yeah, V52 is non-toric, but we didn't actually try too much to do that. Actually, no, one thing we did, this whole business with the problem 2 brains works even for V52. That works very neatly. But yeah, we didn't try to do the whole computation of the density so far.
I see. Okay. And so as a coset, it's SU3 modeled out by SU2 cos1. What is the variety?
V52, you mean?
Yeah.
What is that? Sorry, let me check something. I don't remember by heart, to be honest.
But it could be that it has a symmetry SU3 cos SU2, right? Is that correct?
Maybe
possibly.
I would suggest we could have this discussion in the off the record part. So. But did we have more questions?
Yeah, I'm happy to
Andrea on what has happened last hour. Okay, well, I would say in that case, let's thank Andrea again for this nice talk.
Thank you.
We can move on to the unofficial part.